d'être ici en si grand nombre. C'est toujours un plaisir. So, good morning, everyone, and welcome to this latest edition of our monthly meetups organized by CLIQ-ai, the Computational Linguistics in Quebec Consortium. So my name is Fabrizio Gatti. I'm a programmer specialized in NLP, and I work at the University of Montreal. Today, the topic is knowledge graphs. So we have two talks from two friends of the consortium, two members actually, including the lead researcher, Jian Yunyi. First, we're going to hear Jian Yunyi speak about the infusion of knowledge graph into text representations. Which is obviously a hot topic and a central topic for our consortium, which is interested in injecting knowledge into NLP systems. And then we're going to hear from Bang Liu from Mila and University of Montreal, who's going to talk to us about bridging large language models with knowledge graphs. So before we start, I'm going to ask everyone to mute yourselves, as usual, to avoid distractions. And usually we proceed by taking the questions, 5 to 10 minute question period at the end of the presentations. So if you have a question during the presentation, I suggest you write it down so that you can ask it later. You can ask it in French, and we're going to translate it if necessary. So we're going to move now to Jian Yunyi's presentation. Jian Yunyi, of course, is the lead researcher of CLIQ-ai. He's a full professor at the Department of Computer Science and Operations Research at the University of Montreal. He's a member of RALI, my laboratory, dedicated to natural language processing. You all know him, so I don't need to make any further introduction, just to say that he's really the lead for our consortium. So Jian Yun, the floor is yours. If you have any additional remarks, of course, you can do it. And just make sure that you can share your screen. So right now we have the editing mode, so you can switch to presentation mode whenever you're ready. Thank you so much.
All right. So yeah, good morning to everybody. It is really a pleasure to have this regular meetup with people in CLIQ-ai. So as you know, CLIQ-ai has been in preparation for a long time, and we are almost at the last step, and we hope that we'll be able to submit in the coming weeks. So this is what we hope. This is the last verification in administration stuff. So today's topic, as Fabrizio said, it is about knowledge graph. So I'm going to just survey a set of papers that I found in the literature to present how knowledge graph can be infused in text representation. As we know, we have text that should be represented somehow. We can use BERT or GPT or whatever to just read the text and create the representation. But also we have knowledge graph assigned. So the goal here is to inject some of our prior knowledge from knowledge graph into text representation. So we are going to see how this has been done in the literature, and we're going to discuss at the end how what's the problems that are remaining, and how we can think about how we should deal with that. And by the way, this is a central topic of CLIQ-ai because our proposal or our themes of research topic in CLIQ-ai includes infusion of knowledge graph, trying to use the prior knowledge into different applications. So this is highly relevant.
You are muted, Professor Ni.
Okay. Right. So I'm sorry. So we know that the language models can do a lot of things, and this is a current approach that we typically use in natural language processing. But also we have to understand that even though language models can capture some word knowledge implicitly, because a lot of the text will describe such knowledge, but we can also understand that a lot of pieces of knowledge are missing from from texts, and this is because we will not necessarily describe the knowledge that everybody knows in the text. So a lot of common knowledge may not be described in the text, and it will be quite difficult for language models to capture such knowledge. It is also possible that the specialized domain knowledge will not be described because specialized people will assume that everybody knows that in the domain. So we are not going to repeat that in the text. And this is the case for medical knowledge, for example, and you will not describe the whole knowledge body of medicine in the text, right? And it is also the case that knowledge captured in language model is very noisy because it is quite difficult to distinguish what is true and what is not. So in that case, knowledge graph that we captured, we established by domain experts can help to say this is a part of knowledge that everybody agrees on in the domain. So that can be part of the true knowledge that we can add into text representation. So this is the purpose of trying to use knowledge graph into text representation. Yeah. So the knowledge graph, we know it is another way to represent what we know about the world. So we can represent the knowledge of the domain established by experts. We can also represent our word knowledge in about everything. And it is a kind of a synthetic knowledge, which is not necessarily the first level knowledge, but can be synthetic, generated by experts. So we have a higher level knowledge, which may not necessarily be found in texts. So the goal of using knowledge graph in text representation is to enhance that representation so that we will represent more things in the text representation instead of just the words or the surface knowledge that we can see in the text. Then the question is how we can infuse knowledge from knowledge graph into text representation. So that's the central question that we will address we will look at in this talk. And there is a good survey paper about the different knowledge graph infusion approaches and the different tasks. So we can see that the knowledge source may be various. That can be linguistic knowledge, encyclopedia knowledge, or common sense knowledge, and so on. And the knowledge can be of different granularities. So that can be about text, about terms, entities, and so on. And they can also be used in different applications for text generation, for entity-related tasks, such as entity recognition, and so on. You can find on the right side the different models that have been designed to deal with different tasks and to use different types of knowledge. I'm going to talk about a few of them and try to pick some typical approaches in different groups. So when we think about the knowledge graph and the text, the goal is to fuse them somehow. So there have been some naive approaches at the beginning, trying to create representations from text and from knowledge graph separately. And we have a lot of different approaches. for that. For text, typically we can use BERT. Now we can use GPT as well. For knowledge graph, there are different graph model that is based on graph structure. And the typical approach is called TransE, which tries to determine the embeddings of a node and the relations, trying to optimize some objectives that I will show you later. And this will create representations for the nodes and for the relations. So once you have those nodes that correspond to the text, then they can be put together. So that's the basic approaches. Later on, it is found that this basic approach may not incorporate the interaction between text and the knowledge. That is, they have been encoded separately. So some other approaches is trying to combine the two encoding processes somehow. So I'm going to show some of them. So one approach that I put here is to say when we have the knowledge graph, how we can create the word embedding. So this is some early work, and one of the approaches is retrofitting. So I'm just going to describe the principle. So the principle is to say we can try to constrain the word embedding training process such that related words are going to be closer, to have more similar embeddings. And we can use any knowledge graph or basically synonyms to add some constraint in the building process of embedding. And there are some other variants, such as the work of Yu and Dretz. We also applied that approach in medical information retrieval in early days. But here, we only try to use the knowledge graph as a kind of a constraint. And later on, we really try to have a knowledge graph with some structure. And we want to build representations for text by infusing such relations between different entities into the building process. So here is one work that I mentioned that has been done by one of my students some years ago. The model is called VGCN BERT, trying to combine GCN and BERT embeddings together. So the idea here is to say we have a kind of knowledge, and here in this particular case, the knowledge graph is created between different documents, different entities using mutual information. So we try to build first the word knowledge graph or vocabulary knowledge graph. This is not based on a linguistic knowledge graph, such as a WordNet or whatever. So it is built just using mutual information. So you can imagine that the different words may be connected according to mutual information. So this is the knowledge graph, kind of knowledge graph used in this case. And then there is a GCN representation created from such a knowledge graph. That is, suppose you have a subgraph containing a few nodes related by mutual information, then it is possible to build a representation using GCN graph convolution network, which is a known technique. So you build that on different subgraphs. Then the infusion process is that once you have a sentence, you will try to determine what words appear in such or such a subgraph. And then there is a combined representation, which is shown here. You have a word embedding and also the embeddings created from different subgraphs, because you know that those words appeared in the text and is included in that subgraph. So those subgraphs will be encoded by some representation here. And what is interesting in this work is that instead of just concatenating those representations and take them as the final representation, This combined representation is submitted to a transformation process, submitted to transformer using attention several layers, and in such a way that the node, which is words at the beginning, will interact with the node representation from the graph, so that the final representation will be a combination trying to allow interactions between those different representations through attention. So this is the basic idea. And once we have that final representation, the task looked at in this study is text classification. So we can classify text into different sentiment or to detect hate speech from a text. So those are some applications that are tested in this paper. And just to show you one example, so suppose that we have a comment about a movie. And if you read the comment, the first part of the sentence is quite negative, but then there is a very positive one. So the whole comment is very positive about the movie. But because of those words, smug and repetitive, using BERT, it will classify this as a negative review. But indeed, it is positive. And using the approach that I just described, it is indeed the case that the model can classify this comment as this review as positive review. And here we try to see how the attention is distributed. And we just look at the CLS, the special token, how much this special token is paying attention to different the words and also the representation from subgraphs. So this is the latent nodes. And we're trying to match those latent dimensions to different words, trying to understand what's the main meaning of each dimension. So some of the dimensions, as you can see, is about boundary, innovation, and so on. So this is a very fuzzy mapping to those words, because we want to understand a little bit how, what are the meanings of different dimensions. And then looking at the attention distributed over those different dimensions, we can see that this is a bird in orange. Of course, there is no latent representation from the graph, so the attention is 0. And the most attention is paid to the last word, do. But once the VGCN BERT is used, we can see that the attention is quite evenly distributed over not only the words, but also over the representation from knowledge graph, from the graph itself. So this is just one example to show that indeed those nodes from knowledge graph represented in this way played some role in the final representation. So the fact that we have allowed them to interact will add some additional knowledge. We also compared with the vanilla VGCN BERT, which just to say we will not allow interactions, but just to combine them, concatenate them at the beginning. And we showed that this is not as good as VGCN BERT allowing interactions. So this is just one study trying to show that there may be some interactions between text and knowledge graph. Okay, so what I just showed is that the knowledge graph that we created may be incorporated into the text, and the knowledge graph can be modeled using different ways. So I mentioned the trans-E, and indeed this is one of the traditional way to encode a knowledge graph so that every node and every relation in the knowledge graph will correspond to an embedding. And you have a lot of other different approaches, including rotate, which one of my students developed. GAT, which is Graph Attention Network, and Graph Sage also trying to use the attention mechanisms in encoding the node and the relations. Now, this is about knowledge graph embedding, and about text embedding. You also have a lot of different approaches, including typically a BERT. Now, about injecting the entity embedding that you found in knowledge graph into text, there is another a very interesting study called ERNIE. And in ERNIE, instead of just trying to use the words in the text to create the embeddings or representation for a text, some prior knowledge is added. That is, typically you have some entities that you can recognize beforehand. For example, the personal names or the organizations or some entities containing several words that can be added beforehand, and those entities correspond to some embeddings, and so those embeddings will be aggregated into text before running the BERT embedding. So this is another way to incorporate the node representation with the words and put them together in the BERT encoding process. So the principle is very similar. So here is some details about ERNIE. And I mentioned transit E. By the way, this is the objective that we try to optimize. So we have embedding of a head entity, and we have the embedding of relation, and we also have the embedding of the tail embedding. So the principle is to say, once I have the head, I add the relation, I should be able to find the tail entity. And then you can look at this figure. We have typically text representation, and that will go on. But in some up layers, we will add the entity encoded by transit E, and this embedding of the nodes will be combined with the text embeddings that were created, and then that will go several layers to combine or to infuse the node representation with the text representation. So that's the principle. So you can look at more details here. We have the word representations here, and we have the multi-head attention for the nodes so that they can interact and infuse somehow in the in this process, and that can be done at for several layers. So the aggregation, I'm not going to into the detail, but the principle can be understood from this figure. So this is the first group of approach, trying to mix up or to fuse the representation of a text and the knowledge graph, and then trying to combine them in the encoding process. Another common approach trying to encode the text and also knowledge graph is to use multitask learning. That is, you assume that we have some encoding objective for text, which is can be the masked language model, such as predicting the masked token, or as auto-regressive objective trying to predict the next token. But whatever, this is trying to encode the text that you are trying to deal with. But we also have the knowledge graph objective. For example, the transit E model try to look at the relation between head entity and the tail entity through relation. So this is some another objective. So the goal of multitask learning is to combine those two objectives and to learn both the encoding for text and for knowledge graph at the same time. By the way, the knowledge graph objective can be applied to a lot of different types of knowledge graph. So we may have the relation between entities or linguistic knowledge such as dependency. And it is also possible to put that. And it is even possible to encode some senses if we have the knowledge about that. So I'm going to talk about a few of them. One typical work is called Kepler, trying to encode the text that we read and also the relation between entities. And between entities, say about so I'm going to show one example. So here we may have one person who is related to different other entities. For example, we know Kepler is German, and well, his occupation is astronomer, and so on. So we have different relating entities to that person. So this is the knowledge graph used in this work. Now, as I said, we have on the one side, we have a text encoding process. So we may have the objective for that part. And we also have the second part, which is encoded from knowledge graph. And at the end, we'll combine those two representations. So the final objective is a combined loss function. We have knowledge graph encoding, and we also have mixed language model encoding objective as in BERT. And by the way, the encoding of knowledge graph not only use the nodes, but also the description, because we only if we only use this node as Kepler, we will not have a lot of knowledge. But in this case, not only we have the node, but also we have a description, and there is a sentence or a few sentences describing who Kepler is. And this is very useful to create a rich representation for that knowledge graph. And this is what is used in this case. I am going to talk about another work, since BERT. As I said, it is possible that we incorporate some semantic meanings in the encoding using some relevant knowledge graph. And in this case, the sense is created by the synset in WordNet. So we know that, here we have this bus, and the bus here is type of food and artifact and so on. So we have different super senses about the word bus, and the same thing as chocolate and so on. So the idea of since BERT is to incorporate this meaning, the super senses, in the encoding, so that the terms or the words that are under the same super sense will be closer in the embedding space. So here, if we just use BERT, then we will have only one objective, such as predicting a missing word or predicting the next word. So this is traditional text encoding. But now in SenseBERT, the sense is added as a second label. So not only we try to predict the word, but also the sense of a particular word. And this is the additional objective added. And again, in this work, multitask learning is used to combine those two objectives. Here, I will show very quickly what's the effect of this in training. So we can see that in the embedding space, we may observe that, well, here are some adjectives and so on. So those words are grouped together, and we have the nouns that are grouped together in some space, subspace. And in the right hand side, we can see the different places for different nouns. So we may have abstract nouns and the concrete nouns separated in different subspaces. So this is just to show that by adding the senses, it is the terms, the words may be naturally put into different subspaces closer or further away from each other. And this is some I'm just going to show one example. So suppose we have the sentence: the team used the battery of the newly developed gene probes. So here, battery is not an object. So if we just use bird, that will be classified as an artifact battery, such as a car battery and so on. But in this case, it is not this interpretation, but it is another interpretation which has been found by Sinsbert. And again, in the second case, 10 should leave the ringers standing in the circle 1 foot ahead of something. So here, foot can be just interpreted as the distance. So if you use bird, that will be considered as the quantity. But here it is not. It is really the foot, the concrete foot. So the foot here is a part of the body, and which can be found by Sinsbert. So this, those are just some examples to show the effect of adding the semantic construct in the embedding process. There's also a work that I'm going to do, just present very quickly. So instead of injecting knowledge into the representation, one problem is that once you inject a lot of knowledge into the text embedding process, then there is a problem of catastrophic forgetting. That is, the embedding process that you created with a lot of text will be heavily modified so that you will forget something. So instead of doing that, instead of modifying the initial embedding, in this work, they use the adapter idea. That is, we keep the same embedding process for text, but we also add some adapters, which are small transformer architectures that will be used in as complements to the initial word embedding or word encoding process. So at the end, you will have both. You will have the language model, and you also have a series of adapters, and those two models will be used together. Okay, so that's the basic idea. I'm not going into detail about that, and that has been tested in some classification task or named entity task detection task, and this showed some improvement. And the third work, so the type of work that I'm going to talk very quickly, is trying to encode, trying to put the entities of knowledge graph directly into text, so that they will be encoded together in the text encoding process. So one typical model is called a K-BERT, and you can just look at this figure to understand what's going on. So suppose that you have a knowledge graph, and you read the text, which is the first line. Tim Cook is currently visiting Beijing now, and you recognize that the Tim Cook is the CEO of Apple, and then you just add this branch into the text by adding some additional information picked from a knowledge graph and connected to the name entity Cook, so that you will have an enhanced knowledge text. And then once you have this enhanced text, you just apply the normal encoding process of a text using masked transformer encoder, which is similar to BERT. So this is the basic idea. And the way to add the related related entities and the relations into the text is like this. So you have your original text, which is marked by the position here, but also you create some additional paths so that in addition to have the original path to read the text, you also have some additional path going through the relations that you added. So you can add something about Cook, about the Beijing, and so on. So this is how you can create additional sequences of a text to enhance the original text. And then the encoding will go through different paths. If, for example, if you try to predict the masked entity, suppose that you are masking Apple, then you will have to predict the Apple from this path. Or if you try to predict the Cook, then you not only you have the original context, but also you have the additional context of Apple and so on. So that's about what we can observe in the literature. Now, what are the problems that we can observe? So typically what we can observe is that we assume that entities in knowledge graph have been correctly linked to the text. That is, when you see Cook, you know what is the relevant node in knowledge graph. And we assume that this has been done correctly. And then you also have a process trying to determine what is the relevant subgraph. Typically, we'll just go one hop and two hop around that entity, and that will get some small subgraphs. Then the key question is whether this process of trying to extracting subgraphs is really a good process. And this is very often assumed that we can do that correctly. But indeed, in practice, we observe that it is quite easy to get the wrong knowledge that will be mapped to wrong entity, or you will add the wrong relations into your text. And this is very problematic. So instead of adding useful knowledge, you are adding more noise. So one example that I show here is, suppose that you are reading a text. Obama visited Japan and met with the Prime Minister. So we know that he acts as President of the United States. So this relation from knowledge graph that says Obama's function is the President of the US. This is correct. This is the relevant knowledge to be used in this context. But also in the knowledge graph, it is easy to find another relation around the entity Obama, such as a spouse, is Michelle, and all the other family relations. But in this case, this is not relevant to understand this sentence. But it is very difficult to distinguish between those two relations. So if we just use one hop relation, then both will be added. And this is very problematic. So a key question is to try to select the relevant knowledge to put into the text. I'm not going into detail about that. So typically, the selection is done using attention. So the assumption is that we have a sentence which will correspond to create some embedding. And using that embedding of a context, we will select what are the neighbors around the entity that are similar, have some attention weight with the context. And we will select some neighbor nodes having a strong similarity according to attention to be aggregated into the text. So this is the typical approach. So we assume that attention can detect the relevant neighbor nodes. But this is not easy to do because we don't have a lot of supervision to train the attention estimation in this case, because we don't have the training data telling you, well, in this case, this is the relation to be used, and in that case, you should not use that relation. There is no such resource. So one work that we did some 2-3 years ago is to say, can we build an explicit selection network trying to determine in that context, is that knowledge, a piece of knowledge or relation relevant to the context? So there is an explicit selection network built from there. And the one interesting aspect is to label the usable relation. So suppose that you have a triple head, relation, and tail. And once you have the head corresponding to text, an entity in the text, can you determine that the tail is relevant in this context? So you need some annotations to build the selection network. So here, the idea of pseudo labeling is to say, once we have the context and the response, we don't know what the relation is relevant. We'll try to look at the usefulness of different pieces of knowledge. If by adding a knowledge that is a triple, we can improve the matching between contexts and the response, then we assume that in this case, this piece of knowledge is useful. And we will add some pseudo annotation on that. And this piece of knowledge will be identified as a positive example. So in that case, we can create a lot of pseudo annotations, and that will be used for training selection network. So this is the idea used here. And I'm not going to talk about the different applications. So we can assume that in different domains, we have a lot of knowledge graph. And they just show one example from medical domain. So we may have this entity related to this site and associated with different functions and so on. So this is really a domain with a rich knowledge graph. So some of the studies try to incorporate medical knowledge into different tasks, for example, for text classification and so on. So you can imagine similar approaches as what I presented just before. So I'm not going into details about that because I'm out of time. So I'm going to wrap up. So the final, so we see there are a lot of approaches trying to inject the knowledge graph into text representation. And what we assumed, as I said, is that we have a very good mapping process trying to map the entities from text to the entities from knowledge graph. If we have indeed a very good mapping process or entity linking process, then I would say half of the task is done because you are really you really know what is the right entity in knowledge graph, and you will be able to find the relevant neighbors to be incorporated. But indeed, this is a problem. And in medical domain, for example, it is very difficult to determine what is the medical concept involved in a sentence, because you can write the concept in different ways. And you can just imagine that we have a lot of different synonyms. And also, if you are not a medical specialist, you will write the concept in a different way, just using everyday language. So the concept is implied instead of explicitly expressed. And this will make this mapping process extremely difficult. But this has not been investigated so much. So entity linking is considered as a separate task. But indeed, in the application, such as question answering, information retrieval, you have to consider that. And another key problem is the selection of relevant part from knowledge graph to be incorporated. And this selection process is also some weak part because if irrelevant elements from knowledge graph are selected, then you can't imagine that the knowledge graph can improve the text representation. So this is the key issue that we have to deal with. So that's it. I presented very quickly the existing approaches proposed in the literature, but we see also there are a lot of remaining problems that we have to address. And I think these are the key problems that we need to address in the future. Thank you very much.
Thank you so much, Jian. Very interesting. We have already answered some questions in the chat about Jian's presentation, and I think that we have time for one additional question, unfortunately, because we're a bit short on time.
Yeah.
And I think that in the chat we have a question which I'm going to read out loud. Don't knowledge graph enhanced embeddings require pre-existing expert crafted knowledge graph? Or are there reliable approaches for automatically generating these knowledge graphs from text that is unstructured?
Yeah. Well, it depends on the application. I show the different types of knowledge graph. You may have knowledge graph created from linguistic resources. You may also create a knowledge graph which contains the links between different documents. For example, this document, this paper cite some other papers, and this can be used as a kind of a knowledge graph. And the utility of such a knowledge graph may be different. So if you have the knowledge graph about the documents, it can be used to predict what are the relevant documents to put in the reference, for example. And this is typically done in the literature. But now if you try to deal with the meaning, the senses, then very likely you have to use some linguistic resources. So different types of knowledge graph can be useful for different tasks. So we're not talking about the same task. So you are really dealing with the specific task in the domain. And you have to use a relevant knowledge graph. And there is no unique knowledge graph. There is a large set of such ones. Yeah.
Thank you, Jian.
Yeah. See another question?
Yes, there are many questions actually in the chat. I think that we're gonna run out of time. For the large language models, I suggest that we wait for Bang Liu's presentation, which is obviously on that topic. But there's an additional question that I want to read to you, Jian. A participant is asking, when we integrate the knowledge graph information in these models, isn't there a risk of degrading the linguistic characteristics that are already there? Yeah,
that's possible. So this is why there is adapter architecture. That is, we will not destruct the knowledge structure that is already captured by language model, but we will build another model aside, so that the two separate models can be combined later.
Yes, that's the idea. Actually, the hope that we don't degrade the model whenever they represent words in the traditional way and when they generate text as well. So we don't want to perturb that while we're learning additional things.
Exactly.
Thank you so much, Jian. I think we're going to move on to Bang Liu's presentation because we're a bit short on time. So I thank Bang Liu for presenting this presentation today. It's very, very kind of him. So Bang Liu is an assistant professor at the Department of Computer Science and Operations Research here at the University of Montreal, and he's also a member of MILA, as you all know. He has published a ton of papers. He's an extraordinarily accomplished researcher and professor. We're very lucky to have him today. And he's going to present a talk titled Bridging LLMs with Knowledge Graph. So Bang Liu, whenever you're ready, the floor is yours, and you can share your screen and your presentation whenever you're ready.
Thanks a lot, Fabrizio, for the introduction. So let me share the presentation. So can you see my screen and also hear me clearly?
Yes, absolutely.
Okay, that's great. Thanks everyone for attending this course. I'm very glad to have the chance to present here in this CLIQ-ai meetup. So today we're going to, I'm going to briefly introduce a literature survey I made on the topic of bridging large language models and knowledge graphs. So I think many people are interested in like knowing how they are going to connect with each other. So as we know that nowadays there are so many different large language models are trained and developed every day. So they are briefly like changing the world and changing many things we are doing. So if we review like what happened in 2023, it is a really exciting year for the development of natural language processing for the AI techniques. So basically, like ChatGPT is launched at the end of 2022, and after that, people are getting very excited. Like different companies propose their own language models, like Google's Bard, and then Gemini around the end of 2023. And Llama proposed, like Meta proposed their Llama family models and OpenAI's GPT family. And it's not only limited to text generation, there are also multimodal content generation. So for example, Jian, Pika for video generation, and like there are some for like audio, the like text processing, and also image generation like Midjourney, which is quite popular. And it's not just limited to, let's say, 2023. Actually, there's a long history about the development of language modeling, and there's a relatively short history about a large-scale development language model. So basically, a relative large pre-trained language model, what we call is like since the release of BERT, so in 2018. So in this figure, this is a very nice figure is from the survey paper, a survey of large language models from Renmin University, and also Professor Jian is also one of the authors here. So here they only limited the models with a size larger than 10 billion. And what we call a really large language model, it usually refers to models with parameter more than like 100 billion. So here with over 10 billion, there are so many models here, like since like T5 from Google, then we have GPT-3. And after that, we have different variants and also like, let's say, instruction GPT, verb GPT, and so on. And also it's not only limited to OpenAI, there are models from Google, from like Pangu, and also not limited to Transformer, like the RWKV is a large language model with different architecture other than Transformer. So like the research about large language models are hilarious. And then another name about such kind of peak models, which we call the foundation model. So actually, if you think about how NLP tasks are performed before, usually we have different tasks, right? We have named entity recognition, relation extraction, like sentence classification, chatbot, recommender system, dialogue system, and so on. So it's like what we do in the past time is we train a new model for each single task, even for each single data set, right? And to achieve the best performance. But people found that like if you train a relatively large model, and if you like do some self-wise pre-training based on different modality data, the mainstream is text, right? And other than that, you can also do some learning on images, speeches, some structured data like graphs, knowledge graphs, and also 3D signals and so on. And after this pre-training stage, you get an initial model, what we call the foundation model, which actually acquired some general ability from diverse data source or knowledge source. And after that, you can do some fine-tuning or adaptation process so that it can perform even better on some specific scenario or tasks you need, from question answering, sentiment analysis, to information extraction, captioning, and instruction following, and so on. So it depends on where you want to play this, like want to let this model to take some effects. And it's not limited to research tasks. It's actually impacting the real-world applications, and it's also not limited to text processing. There are many different models like developed for game industry, like for building intelligent NPCs, for example, Conf.ai, Involved, and so on, and for generating multimodal content like Midjourney we just mentioned, and delta E2 noise, like we have delta E3. And there are also like for sound, for music processing, generation, and so on. So they span diverse range of different domains in the real world industry. So obvious question is like, the language models, they perform so good. Do we still need knowledge graphs nowadays? So the first claim is that even though large language models are awesome, but they're not perfect. So there are several like core challenges. For example, the well-known hallucination, which means language models can produce like some incorrect information, which is hard to capture by human beings. And they are not very cheap to train and run. There are costs. Each time you query a language model, it will take time, it will take some money. And it's difficult to fix and update its knowledge. And it's hard to audit and explain the generation results. Also, like if you query the same query to the same model for several different times, maybe you can get inconsistent answers. And it's also not perfect in processing low resource languages where we lack enough training data for different tasks. And there are some like coverage gap on long tail facts or tasks. So let's first talk about the hallucination problem. So that means there are moments when large language models, they give seemingly like logical and fact-based answers that are entirely wrong. So like machine learning professionals, they call this phenomenon as hallucination. So here this image shows a simple example. A user like inputs, please explain to me what an LM is. So the current version, which is not today's version, I think this figure is from maybe early last year. So the ChatGPT says an LM or Master of Laws is a postgraduate degree in law that is typically pursued by individuals. So you can say this is totally wrong because like the model doesn't know what this LM refers to, but explains it like seriously. It looks like it really understands this concept. So if a user has no knowledge about LM, he maybe buy it and make wrong decisions. And this is another example from the New York Times. So if you ask it, like ask ChatGPT, when did the New York Times first report on artificial intelligence? And you get some answer. So if you compare this with what is true, you can see for this single question, it made several factual mistakes. So it's not like February 1950, it's November 1950. And the title is also different. And the problem of hallucination may be even more sensitive and like critical in some important domains. For example, law, health, and finance. So there are many real-world cases where like language models make hallucinations in solving the like questions in this sensitive domain. So for example, if you made wrong facts in the healthcare domain, it will be like have very bad effect for the patients. And hallucination is not the only challenge. Large language models are also expensive to train and run. So the computer scientist Zhendong Vandersik, he's the co-founder of Wikidata, and so he made a comparison between like searching Google search engine, a knowledge graph, or ChatGPT. So give a simple query like who created the score of others. So language models like ChatGPT may take 5 seconds to answer this question. And if you directly search Google, it may take like half second. And if you directly search Google like wiki knowledge base, it will be even faster. You only take like 0.26 seconds. So you can see in different situations, like the cost of different ways to answer the question can be dramatically different. And another issue is that large language models, they are unaware of any events that happened after the training. So if you only use this model without like equip it with any external tools, like with search engine and so on, you just ask this model. So let's say, who is MBA MVP in 2023? And the model may say like, I'm sorry, but the model like developed in early 2021. I don't know the knowledge about this. So because like it lacks the updated knowledge, like things happened after the model is already trained, right? This phenomenon is called like the knowledge cutoff. So we're talking about, do we need knowledge graph? So what is a knowledge graph? So this is a typical image about how a knowledge graph looks like. So knowledge represented as entities, urges, and attributes. So for example, we can have a personal entity that's showing that Tom watched Ghosts of the Abyss. And we have like in a knowledge graph, we have some key concepts to say the different entities, they are represented as nodes in this graph. They're representing something in the real world. And the urges essentially represent different types of relationships. So for example, something is directed by someone. An attribute represents something about an entity. So for example, the name of a person. An ontology is like definition of possible types of entity. For example, we have like human beings, we have animals, we have like different objects. And so an entity representing a person with name attribute James Cameron. So in this like the spoof of another person. So we can see from this simple example, we observed several different entities. We can see how they are related to each other. And for each entity, what type of attributes he or she can have. And some well-known knowledge graphs like DBpedia, Freebase, Wikidata, Yago, and so on, and also like some common sense knowledge base like ConceptNet and so on. So these are like they cover different domains, and they are sometimes extracted from the Wikipedia, or they are built by the community of volunteers, including like the information from web pages and so on. And aside from, let's say, the knowledge bases in general domain, we also have like enterprise knowledge graphs. So in this case, like enterprise knowledge graphs, they are typically internal to a company, and they are applied for some specific commercial purpose. So let's say if you are building a knowledge graph for web search, like the company Bing, Google, and so on, or Airbnb, so mainly like your information source will be mainly from the like the company itself. So the user customers data, the interaction record of them. And social network like Facebook, LinkedIn. So you can have a social network knowledge about different users, their interests, their friendships, their like follow relationships and so on. And financial knowledge graph, like from Bloomberg, Capital One, Wells Fargo. And different applications, it depends on like the, let's say, what type of company it is, right? So what kind of commercial activity it is doing. So they can do searching or recommendation or personal agents and so on. So this is an example. So this is our prior work on in like 2020. We constructed a large-scale ontology with hierarchical concepts, categories, entities, and topics and events. Like from they are constructed from the user queries and feed stream articles, web articles. So in this case, like we can label different level of text to, let's say, to a query or to a concept, and we can better infer the user's intention when the user inputs something in the search engine. And also we can better understand both short query and long documents so that we can improve the performance of recommendation. And this is another example, the product knowledge graph from Amazon. So here we can see that it shows two different product entity, the Tide plus Frap, Tide plus Co. So they're like two entities from the same brand. So they share many common attributes, and also they have their own unique feature. So in this case, like based on a customer's, let's say, the browser history is like searching history is purchase history, we can better understand like what kind of products the customer may want to buy, so that in the e-platform, you can have some better experience about recommending the user with something maybe he or she is interested in, so that improves the like products selling record. So we can, let's say, compare the pros and cons for large language models and knowledge graphs. So for large language models, its pros is that language models have general knowledge and it's strong in language processing. It can understand different type of text, and there's a strong like generalizability, like it can be transferred. It can handle diverse tasks, and it also has cons. So the knowledge it contains is implicit, like learned in the ways. They can make mistakes. They can have the problem of hallucination and indecisiveness. And their black box models is hard to explain the prediction, the output, and they lack domain or specific new knowledge. And for knowledge graphs, so they're structural, right? They're graphs, so they contain structural explicit knowledge. They're accurate, so and they are helpful for decisiveness, and they're easy to interpret. They can be constructed to represent the domain-specific knowledge, and they can be updated to contain evolving knowledge. But they can have incompleteness. We cannot assume that a knowledge graph contains all the knowledge, and they lack language understanding ability, and they also don't contain unseen facts. So if you compare like both of these worlds, it is obvious that maybe we can combine both worlds to maximize the power to give benefits to like mutually. So this figure is from this very nice way. So unifying large language models and knowledge graphs, a roadmap. And many of our materials is based on this survey paper. So in this survey, like authors categorize 3 different frameworks to like unifying knowledge graphs and language models. The first way is knowledge enhanced LMs, which means we're using knowledge graph to improve the performance of large language models on different like tasks. And inversely, we can also utilize large language models to improve the quality of knowledge graphs. So this is like LM augmented knowledge graph. And also we can mutually let them help each other and jointly learn better representations about both LMs and knowledge graphs. So this is synergized large language models combined with knowledge graphs. So we'll briefly like check how each different categories may work together. So let's start from the first type. So how knowledge graphs can help with large language models. The first way is we can use knowledge graph to improve the improve the pre-training of large language models. So for example, we can integrate knowledge graphs into the training objectives, or we can integrate knowledge graph into the inputs, or we can utilize it to construct instruction tuning dataset. So for the first way, injecting knowledge graph information into large language models training objectives while text knowledge alignment loss. This is like what Ernie has done. So you can see the left figure, we have the input text. Bob Dylan wrote Blowing in the Wind in 1962. So we have a text sequence. We also have the corresponding entity from a knowledge graph. And in our training objective, we want to align the text representation for Bob in the text, as also like the entity from the knowledge graph itself. So this gives us the text knowledge alignment training objective. And the second way, injecting knowledge graph information into large language models inputs using graph structure. So the right figure, so we have the input text. Mr. Darcy gives Elizabeth a letter. So what they did is we turned the original text into a, let's say, word co-occurrence graph. So if 2 words co-occurrence in a sentence, we can construct a co-occurrence urge between them. And if an entity is contained in a knowledge graph, we can also include its neighboring nodes to form a local knowledge graph structure. So we merge this text graph and knowledge graph, and we jointly learn the representation, and we feed it into large language models so that we can, let's say, mask different entities in the, let's say, text or in the graph, and we can use the context to predict any of them. And the last way is like we can like linearize a knowledge graph and try to create some instruction tuning dataset. Another important framework to integrate external knowledge to help with a large language model is what we call the retrieve augmented generation. So this figure from paper 3 shows a framework. So you can see this example. Let's say we have a query. How do you evaluate the fact that OpenAI CEO Sam Altman went through a sudden dismissal by the board in just 3 days and then was rehired by the company, resembling a real-life version of Game of Thrones in terms of power dynamics? So you can see this is a recent hot event. I think it's happening like around the end of last year. And if you directly ask a language model, which doesn't know these like new facts, it may answer without rec. Then it says, I'm unable to provide comments on future events. Currently, I don't have any information regarding the dismissal and rehiring of OpenAI CEO. That's natural because the language model don't know what happened, and it has no context to answer this question, give any meaningful comments. So if we augment the language model with external knowledge by the RAG, by retrieval augmented generation, so what we usually do is we have a search engine, we have a retriever to retrieve external knowledge. For example, there can be some documents represented by some vector database, and we can retrieve this embedding from the query, and we retrieve some relevant document. We get different relevant chunks. Let's say chunk 1, Sam Altman returned to OpenAI as CEO. Silicon Valley drama resembles the Zhengguan comedy, and we have chunk 2 and chunk 3, so different piece of information from the document database. And with this retrieved external knowledge, we can reformulate our query, right? We're not just asking the question, we can further say like, please answer the above question based on the following information. So we provide the information from chunk 1, chunk 2, chunk 3. So with this extra knowledge, the model can say, can like better answer the question. So this suggests significant internal disagreement within OpenAI regarding the company's future direction. So we can say like the core idea is simple. So we need to augment the context information by retrieving some external knowledge. So we can retrieve external documents. We can of course retrieve external like triplets from a knowledge graph, right? So let's say if you ask which country is Obama from, and you have some knowledge retriever, which can extract relevant piece of knowledge triplets to better answer this question. You may extract like Obama born in Honolulu, and Honolulu is located in United States. Then the language model, based on this question and the like retrieved facts, it can answer like Obama is from United States. And knowledge graph can also enhance the language model's interpretability. So when we talk about interpretability, we mean the understanding and explanation of the inner working and decision-making process of a language model. So language model gives us some outputs. We want to know how the language model actually gives these outputs. So this can improve the trustworthiness of large language models and facilitate the application in high-stakes scenarios such as medical diagnosis and legal judgments. So for example, when we do legal judgment, we need to cite relevant case in the past. And when we do medical diagnosis, we need to explain to the patients like why we made this diagnosis, what kind of like factual evidence supports my decision, maybe from our conversation history, maybe from some like published thesis papers. So there are many like two categories of work. One is knowledge graph for language model probing, another is for language model analysis. So we'll see how they works. So this shows a framework for like how knowledge graph for language model probing works. So the idea is that first we can convert the facts in knowledge graphs into closed statements by some template. And then the language models predict the missing entity. And last, we evaluate the knowledge stored in language models prior prediction. So for example, here, like we have, we show a piece of knowledge graph. Then we linearize it into some facts like Obama, profession is president. And we have a question generator, turns it into a question. Obama's profession is what? We mask the answer, right? And we let the language model to predict the answer is president. Then we can compare the answer from this language model with the answer from the knowledge graph. So we can know whether the language model knows about this knowledge, whether the knowledge is true or false. But there are also problems about this kind of methods. So the prompt template, the design may matter. So for example, the prompt Obama worked as the space. So this prompt may be more favorable to the prediction of the blank binary model than another template, like Obama is something by profession. So basically, the performance of the language model can be sensitive to the design of the template, and it includes some manual works there. Another category is knowledge graphs for language model analysis. So basically, analysis aims to answer the following questions, like how do large language models generate the answer, generate the results, and how do the function and the structure work in large language models? So a bunch of the work, they're trying to make the results generated by large language models at each reasoning step grounded by knowledge graphs. So if you ask a language model, which country is Joe Biden from? We hope that language model is not just directly output the answer. Actually, we hope it can pay attention to the relevant piece of knowledge in a knowledge graph so that we know how the answer comes from. So for example, in this example, this figure, it shows this answer is grounded to this subpath. So Joe Biden, colleagues Obama. Obama country is from United States. So we say that Joe Biden is from United States. This is another concept proposed in this paper published in ACL 2022. So the authors proposed the concept of knowledge neuron. So they construct a knowledge attribution method to identify the neurons that express a knowledge fact. So you can see in this figure. So this is like how transformer works, right? You have some self-attention layer. After that, you have the feed-forward layer to further process the hidden representation from the self-attention layer. And in this paper, actually, they consider the neurons in the feed-forward layers as key value pairs. So they are trying to find out which neurons are sensitive to closely associated with a piece of factual knowledge. And they find some way to link the corresponding knowledge with the corresponding hidden neurons in these feed-forward layers. And once we find the alignment relationship between a knowledge fact and the knowledge neurons, what we can do is that, so we can edit some specific factual knowledge without fine-tuning the whole network. Instead, we just need to fine-tune the corresponding knowledge neurons. So we have discussed part one, so how knowledge graphs helps with language models. So the second part is how large language models can help with knowledge graphs. There are different research, for example, language models augment knowledge graph embedding or help with its composition, construction, or text generation, question answering, and so on. So let's briefly go through some of them. The first is we can use a language model to augment the embedding of knowledge graphs. So this is also mentioned in Jian's talk. So we can see. So basically, when we learn the embedding, what we want to do is we want to map each entity and the relation into a low-dimensional vector space, right? So that a language model can enrich the representation of knowledge graph by encoding the textual description of entities and relations. The idea is that, let's say if you have a triplet, Neil Armstrong, born in Wapakoneta. So here we have this name, Neil Armstrong, and we can augment it with some description. So he's an American astronaut and aeronautical engineer. And Wapakoneta is a small city in Ohio, United States. So with this more rich text description, we can have better embedding through a language model encoder so that we can improve the quality of both entities and the relations. So this is quite natural, right? So if you embed some entity or relation just based on the name itself, it actually lacks enough information, especially when you have some, let's say, new entities. You only know the name, but you don't know how it is related to any of the existing entities. But with this enriched text description, even though it is a new, new one, you know, so like this entity is related to or similar to what kind of existing entities. It knows different attributes. So this will give you rich semantic information. And another way is like instead of using knowledge graph embedding model to consider the graph structure, another line is directly employ large language models to incorporate both the graph structure and textual information into the embedding space simultaneously. So the idea is that like we can construct some inputs and use mask rank modeling objective to predict the missing information. So let's say you have for each triplet, you have the head, you have the relation, and you have the tail. So you can mask a part of them and try to recover this masked part using the remaining context information. So in this way, we are doing embedding learning with this mask ranking model objective. So just like how we train BERT. And we can, of course, like utilize large language models to, let's say, perform knowledge graph completion. So one way is like we do what we did just now. So we're trying to use some embedding of both the text and the knowledge graph. So we have some dual representation of these embeddings. Another way is like we directly use the ability of large language models to perform some in-context learning. So we can formulate our task by some prompting, let's say, given head entity and relation, predict the tail entity from the candidates. So this is our task description. And after that, we give, let's say, 5 in-context learning example. So we show the model a few examples of head, relation, and tail. And last, we give our input. We give the head, we give the relation, and we ask the model to predict the tail. This is a typical in-context learning prompt design, which includes the task description, includes the in-context example, and includes your input for this specific question. And of course, like we can directly use a large language model to help construct a knowledge graph, right? So this is just a typical, like classical pipeline to construct knowledge graph. Usually you need to select like the sources of knowledge graph, where you want to, which kind of data you want to use to construct the knowledge graph. After that, the main step for construction is information extraction, including, let's say, the main tasks like named entity recognition or relation extraction, entity linking, and so on. And after that, once you construct a knowledge graph, you need to do the maintenance and you apply it to different applications. So how we can utilize large language models to help with this construction? And in this paper, like the authors tested the ability of language model perform such kind of information extraction with prompt engineering. So basically, the idea is that, so let's say we are given some text and we extract different sentences from the text. And what we want to do, we need to do named entity recognition. We need to do relation extraction, entity linking, and so on. So we can design the prompt. The given sentence is like the sentence itself. And then we say, given the list of the entity, relation, or even the types, so we show the list. And we ask what entity or relation or even the type may be included in this sentence. So similarly, you can formulate different tasks by prompt engineering. So you describe your need, you show the examples, you show the candidate options, and you let the language model to decide what are the outputs. So, and we can, they show that like actually language models demonstrated very good zero-shot performance, which means you don't need even to further fine-tune it on knowledge graph. It can already have this ability. The key is like how you elicit the ability. You need to design appropriate prompts to make it perform the tasks. And instead of like extracting entities relations from external text, you can also try to distill the internal knowledge of the language model, like it already learned from the large corpus during the pre-training stage. So basically, the idea is that you can design some closed questions and you ask the language model to predict the missing information so that you get this new triplets, and they can be merged into your knowledge graph under construction. So this is the general framework to distill the knowledge graph from the language model itself. So we discussed like how language models help with knowledge graph, or knowledge graph help with language model. So they are unidirectional, right? So can we do some synergized language model help with knowledge graph? They mutually improve each other. So the key idea is like, can we jointly like learn or utilize them together so that they can boost each other's performance? One way is what we call the synergy knowledge representation. So we can have like this two paths. You have the text input, you have the knowledge graph input, and you either text or graph attention over both of them, and then you learn some output for both text and knowledge. So this is a general framework, shows how you can have this dual encoder and jointly learn both of them to perform different tasks. Or you can do synergy reasoning. So it's more like the RAG architecture. So you have your input question or query, and the language model acts as an agent. It will, instead of directly answer your question, it may refer to the knowledge graph and find the relevant piece of information and further answer the question based on the retrieved information. So this is like reasoning on graph with the language model agents. So there are also many useful, like exciting future directions about integrating language models and knowledge graphs. So we can see like how we can better utilize knowledge graphs for the hallucination detection in language models, or use it as an external source to validate language models. Or how we can like utilize knowledge graph for editing knowledge in language models. The key is like how to update the knowledge without training the whole model, because the cost of like training or fine-tuning a language model is high. And how we can utilize knowledge graph for black box language model knowledge injection. So we want to enable the effective knowledge injection without training. And the multimodal language model for knowledge graphs. So how we can effectively leverage representation from multiple modalities. So we not only have like text, we also have the images, videos, audios, and so on. So we need to align the information from different modalities so that we can have a richer representation about the single entity or relation there. And how we can better utilize like a model for understanding the knowledge graph structure. So now we are mainly like try to linearize the representation of knowledge graph triplets. So the original structure is transformed into some sentence representation. So can we better utilize the language model to make it directly reasoning over a large graph? And also the synergized language models and the knowledge graph for bidirectional reasoning. So we want to better leveraging the strengths of both technologies to overcome the individual limitations. So that's all about today's talk. And this here I listed the main referred paper in this presentation. So thanks. Do you have any questions?
Thank you so much, Bang. It's quite the portrait. Thank you so much.
Thank you for.
We're a bit out of time, but I think that we have. We'll take an additional 15 minutes to answer questions. There are so many. So, but one question I have for you, Bang, do you think that beside the recording of this presentation, you could make the slides also available?
Oh yeah, I can share these slides.
Great, because there are many people who would like to review your presentation.
Thank you. Yeah, no problem.
Do we know where we will put that? Do you have a space already?
Yes, we'll put that on our website and maybe in the YouTube description if you want.
Good.
So we have a question from you, Chen. Jian, would you like me to read it, or would you like to ask them yourself?
You can read it for me. Thank you.
Okay. So the first question we have, professors, is right now, what would be the most powerful open LLM with which researchers can do research that is open source, essentially?
I think nowadays there are many open source model checkpoints on the web, like Meta's Llama series, right? And also many variants from Llama, like Vicuna, and many Llama variants fine-tuned for specific domain, for example, for medical domain and so on. And actually, yesterday, I think there's another open source model. They're not only releasing the checkpoints, but also the, let me check, the training code and testing code. So actually, I shared it to my class Slack. Let me find it out here. So this one, the OLMO. So from AI2. So you can check this. They released the code which they call the OLMO Open Language Model. I can put it in the chat of this meeting.
Yeah, the field is evolving so quickly that just yesterday we have something new.
Yeah. So I cannot find the chat now, but yeah, you can record the name, which is OLMO Open Language Model. They released the GitHub code. They write the technical report, and they also have a blog talking about this. So I think this can be a very good resource. And also Mixture AI, they release some mixture of expert model architecture, right, which contains, I think, 8 different models combined as multiple experts. So yeah, so I would say now is a very good area. People can do research with many open source information there.
Yes, as long as you have the infrastructure to run those those language models, of course. Another question, Professor Liu, is about retrieval augmented generation, and the question is about catastrophic forgetting, meaning that if we condition the model on some retrieved knowledge, isn't there a risk to forget what the actual knowledge, the language model had already as knowledge within it, and how to mitigate this side effect? Another question from you, Jian.
Yeah, this is a good question. So of course that when we retrieve any external knowledge, so we can definitely have the risk that the knowledge itself may be incorrect, right? So if the, let's say, if the information is just outdated, so we need a mechanism to keep updating the information there, right? So for example, we can retrieve the information from multi-source, and we can weight the importance of different information pieces by not only the publisher, the quality of the knowledge itself, but also the time, whether it is up to date or not. So basically nowadays, when people constructing different applications centric with LLM, it's not a simple research project. It's more like a system engineering. So we need to combine different components to ensure the quality of external knowledge, to ensure the generation quality of the language model itself. So yeah, so basically I think we need some extra module to improve the quality, ensure the update of the new knowledges.
Yeah, I would add that there is a fundamental problem behind that is how we can determine that the additional information is reliable. And this is problem related to hallucination, or once we have retrieved some additional information, can that help solve the problem of hallucination or not, depending on whether the additional information is reliable, is trustworthy. So this is the fundamental problem that we can't solve with a language model used as a black box, typically. So I think there are a lot of things to do in research.
Yeah, I agree. So basically, like the current language model, even our human beings, right? We cannot make sure our answer to any question is always correct. So we need to, let's say, take the generated output carefully to see like how we're going to utilize it, how we're going to further validate its authority, its correctness, especially like for sensitive domains, right? For example, the legal domain or medical domain.
I understand. We've talked a lot during the presentations about additional knowledge injected into the LLMs or produced by the LLMs when they build knowledge graphs. Typically, these are common sense elements, but for specialized domains like the industrials in attendance are interested in, there are specific challenges. When we talk about medical knowledge, they're very rare, very specific. Yeah. Are there any issues when working with these very rare and specific knowledge when we use an LLM that has been trained on very generic information?
Yeah, that is a very good question. So we know that large language models, so AI for science, this is a quite hot domain. So people are working on different domains like biology, chemistry, proteins. So for example, in our lab, some of us students are working on AI for material science. So if we compare the scientific domain and the traditional domain, so there are several unique challenges, right? So first, usually there are like so much high quality labeled data. So because it requires many professional knowledge to label this data, so what we need to do is how can we learn as much knowledge as possible from unlabeled corpus. And the second is there are diverse source, diverse modality, diverse formats. So we can have images, text, we can have different diagrams. We will have, let's say, some in-domain representation, like how we represent the different molecules and so on. So this requires extra knowledge to understand. And they are from different publishers. They have like different papers, right? They have web knowledge and so on. So we need to find a way to, let's say, collect high quality data. So for example, many recent research, instead of just relying on scale up the data size, their emphasis is how we can better learn or fine-tune a language model with relevantly limited size, high quality data. For example, learn from textbook and so on. So I think this is also another important problem. And the third is, it's not only the superficial knowledge, it's more about the reasoning abilities, understanding. So actually, reasoning ability of language model is still a core research problem in this domain. So even, let's say, like the early version of ChatGPT, maybe the current version, they still cannot effectively solve some like simple mathematical questions. So because like the way how language model works is not the way how we do complex reasoning, right? We need to combine this autoregressive generation with many other mechanisms so that we can better reason over external knowledge, and maybe we can better manipulate code, equations, mathematical theorems, and so on to perform more in-depth reasoning and do some long-distance planning.
Of course. Thank you. We also have a question in a person in attendance, Yihong Wu. You can ask your question by unmuting yourself and asking your question.
Okay, and in current slide, there is a part of knowledge retrieval. I just wonder if you can give some details about how this knowledge retrieval works.
Okay, yeah. So I think this knowledge retrieval is actually depends on how your knowledge is represented. So if we are talking about, let's say, just general text knowledge, maybe they're not in the structure of knowledge graph. Then you need to do is to use let's say, some search engine or traditional information retrieval methods, right? So if it's stored in a graph database, then the retrieval can be like some graph search engine. You need to query these triplets to extract the relevant triplet from the knowledge graph database. So I think in different circumstances, you have different implementation about this retriever. It depends on the format, how you store your knowledge, and it depends on like the specific libraries you're using. And
Okay.
there's another type of important knowledge is like the called vector database. So in this case, actually, we're not storing the explicit text or graph. Instead, we do some preprocessing. We split the documents into different pieces, and we turn them into vector embeddings. So in this case, you can use like vector-based retrieval to retrieve the relevant piece, and also further get the original text chunks there.
Okay, I have one more question, because if the knowledge is stored in the KG, for example, like a triplet, so
Yeah.
how can we select the most relevant triplet in this KG? This is also relevant to Jian Yun's presentation about how to select the most relevant knowledge in the graph.
Yeah, so for example, like the most simple idea is that it depends on, let's say you can start from a target entity, right? So in this question, which country is Obama from? So the key entity here is Obama. So based on the knowledge of the language model itself, maybe it knows what is the full name of Obama. We can retrieve the, let's say a part of the subgraph centric with Obama. So let's say if you find the entity in this knowledge graph and you define a distance, maybe I want to include all the relevant piece of knowledge within 3 hops or 5 hops. And then you get a candidate list of the retrieved triplets. And you can further do some filtering to filter out the triplets which is not so relevant with this question. And you get a more truncated tracks without noise.
Thank you so much, Bang. I think we're going to conclude on that. We're out of time. I thank again the 2 top researchers who have had the kindness to present this. I'd like to thank my collaborators at Ivado, as always. And as I said earlier, we're going to put up the recording of this session as well as the slides. I thank everyone. Stay tuned for more news, and I look forward to seeing you all next week or next time. Until then, thank you so much. Have a nice day.
Yeah, thank you.
A nice day.
Yeah, bye-bye.